For two things to be equivalent, that means that they are equal. Let's take, for instance, fractions. We know how to recognize fractions, but, and then, when we're learning fractions at first, we learn about maybe something called part over whole. As far as fractions are concerned, part over whole. And what that means is that there's 2 shaded in squares over a total of 4 squares over here on the left side, right? And then we see here, even though I copied and pasted this, so it is the same size rectangle. And let's say I color in 3 of these smaller rectangles. So there are 3 rectangles colored in. There's a total of 1, 2, 3, 4, 5, 6 of them. And equivalent, again, means that even though these numbers are different, 2 over 4, 3 over 6 are equivalent. They are equal. They are the same mathematically. 2 over 4 as a fraction can be reduced by dividing 2 to get 1 over 2. 3 over 6 can be divided by 3 on top and bottom. And that's how you get 1 over 2. Again, that shows why and how these fractions are equivalent even though the numbers look different. Reducing or simplifying a fraction can be done essentially in one of 2 ways. One by division, which is what we saw, and another is by factoring. 2 is the equivalent of 1 times 2. 4 is the equivalent of 2 times 2. Now, since these factors of 2 are the same on top and bottom, we can cross those out. And that means 1 over 2 is what we're left with. Again, now we're using 2 types of equivalency. One with factoring, right here, and another with canceling or simplifying or reducing. Let's look at number 3 over 6, which again can be factored into 1 times 3, can be factored into 2 times 3. Right now, if we're using 1 as a factor, 6 can be also factored into 1 times 6, but that kind of thing doesn't help here because in order to simplify this fraction, we're looking for factors that are the same. So 1 over 2 is what we're left with. Again, factoring creates the equivalent, and also canceling creates an equivalent. All right? And I want to talk about factoring a bit because we have talked about it before, but it is something that needs more revisiting, which is why we're doing this lesson today. Factoring maintains equivalency. Factoring or rewriting maintains equivalency, and we're going to go through a way to show that. This expression that I have given here, this expression, I'm going to call expression A. 5x to the 7th minus 75x to the 4th plus 25x to the 6th. Now this can be factored by using a common factor of 5x. Let's suppose that. And what we're doing when we factor is we are dividing. We're using division. Let's go back to this example here. If we know that 6 is divisible by 3, then it means 6 divided by 3 equals 2. That's how we get this number right here. If we know it's divisible by 2, 6 divided by 2 equals 3. Right? Again, factoring is a division step. So what we're left with inside the parentheses after factoring out a 5x is going to be 10x to the 6th minus 15x to the 3rd plus 5x to the 5th power. Now what's confusing is this is not factored completely. It's possible to factor but not factor completely, meaning factoring completely means that inside here 10x to the 6th minus 15x to the 3rd plus 5x to the 5th does not have any more common factors in it. That means you can still find something to divide into all three of these terms. Whether it's numbers or letters or both, that's part of the problem. That's part of the issue that we're trying to solve. So 5x is useful, but it is not complete, which is the problem. So let's find the greatest common factor, which is going to be, in this case, 25x to the fourth power. And let's do that division. Knowing what we know about exponents and fractions and things like that, we are dividing the base numbers and we are subtracting the exponents. 50 divided by 25 is equal to 2. X to the 7th divided by x to the 4th means x to the 7 minus 4, and that's how we get x to the 3rd. Same thing on the other side, that's going to be a 3. 75 divided by 25 is 3. And x to the 4th divided by x to the 4th is equal to 1. So there's no x variable left. Plus x to the second power. Because 25 divided by 25 is 1. And 6 minus 4 is equal to 2. So again, factoring maintains equivalency. That means in this expression, which I'll call b, these are mathematically equivalent. That means that if we choose a number for x and plug it in and evaluate it, we're going to get the same thing whether we plug it into a or b, and let's verify that. So verify by evaluating at non-zero values for x. Right, we only need to pick one. So pick a number for x, anything you want to. It just can't be 0. And then we're going to plug this into equation A and I'm sorry. I didn't say, I said equation, but I said that wrong. This is an expression. We will plug it into expression A and expression B, and then we'll see how they evaluate. That means doing all of the PEMDAS, adding and subtracting and things of that nature. So let's take expression A. That's going to be, well, first of all, let's pick a number for x. We can choose 1. That's nice. 50 times 1 to the 7th power minus 75 times 1 to the 4th power plus 25 times 1 to the 6th power. Work this out and you get 0. Right? That's 50 minus 75 plus 25 is going to be 0. And that's expression A. Now let's look at expression B. 25 x to the 4th power, so that's 1 to the 4th power, times 2 times 1 to the 3rd, minus 3, plus 1 to the 2nd power. So this becomes 25, 2 minus 3 plus 1 inside the parentheses. And this is going to be negative 1 plus 1, which is 0. So 25 times 0 equals 0. And this is expression B. Now, since these are the same, we have verified that this factoring is correct. Now, one thing I want to caution, that first, if you want to rewind a little bit and try to verify that first piece that we had, it said 5x times 10x to the 6th minus 15x to the 3rd plus 5x to the 5th. The verification will work for this. So verifying it does not tell you that you are factored completely. It just tells you that you are factored correctly in some capacity. All right. Verification also works for rational expressions, simplifying rational expressions, simplifying complex fractions. You can verify by choosing numbers and checking, choosing non-zero numbers. Let's try another expression, polynomial expression, and maybe we'll do a rational expression. I think I have one queued up here. Okay. So let's factor completely. Again, factoring completely means that you have factored all the way down, so there's no other common divisors. Now this one is a little bit tricky. It's got a lot to it. So we could take this piece by piece. There is no rule that says you have to do it all at once, right? In fact, something like this might be a little bit easier if we do it piece by piece. So let's take that approach. The first thing I want to factor is x, right? I see here, this is x to the 5th and this says x to the 1st. So we can factor, excuse me, x like that and make make this a little bit smaller, a little bit simpler, a little bit easier to look at. I am noticing now, this is the number 6 and this is the number 294. Again, without trying to just find the greatest common factor, they were both even numbers. So let's look at that. Let's look at that and divide out 2. So that's going to make a 2x out here. And that's going to be 3x to the 4th minus 294 divided by 2 is going to be 147. And that's going to be y to the 6th power. So we know this is a 3 and this is a negative 147. A neat little trick is if you take this number 1 plus 4 plus 7, that's equal to 5 plus 7, which is 12. Since 12 is divisible by 3, that means we know 147 is divisible by 3 evenly. So let's factor that out. Let's factor out a 3. That's going to make outside 6x, right? That's from 2x times 3 to be 6x. X to the 4th minus 49 y to the 6th power. And can we factor anything else? This says x to the 4th. This says 49y to the 6th. There is no common variable. There is no other common divisor for any of these coefficients. Does that mean we are done factoring? No, because once GCF is done, there's AC method, which this is not, because an AC method is quadratic. And there's also difference of perfect squares, right? So if x to the 4th is a perfect square, and we have a minus sign, and 49y to the 6th is a perfect square, that means we can factor out using the difference of perfect squares, and which we can. So 6 times x, we're going to start with x to the 2nd power, that's the square root of x to the 4th. We're going to continue with 7y to the 3rd power. That's the square root of 49y to the 6th. And then a plus and a minus. And we are done factoring completely. Let's see if our answer is correct. Right, let's take expression A and expression B. Again, these are expressions. And let's pick a number. Let's choose x equals 2. Let's choose y equals 3, just so we're not, again, we can choose 1 again, but I wanted to show you some examples for different numbers. And this one has 2 variables, x and y, which means we got to choose a number for each. So let's look at expression A first, right? 6x to the 5th, that means 6 times 2 to the 5th minus 294 times 2 to the 1st power times 3 to the 6th power. Right, so 6 times 32, following order of operations, minus 294 times 2 times 729, which is 3 to the 6th power. Let's multiply this out, 192 minus 400,000, 428, 652. And we'll subtract this to get negative 424. Nope, sorry, wrote that wrong. Negative 428, 460. Again, from expression A. Now let's look at expression B. We have it written right up here. So let's plug in 2 for x, 2 squared plus 7 times 3 to the 3rd power, and then 2 to the 2nd power minus 7 times 3 to the 3rd power. On the outside of the parentheses, 6 times 2. On the inside of the parentheses, this is going to be 4 plus 3 to the 3rd power, which is 27 times 7. All of that put together is going to equal 193. And then on the other side, negative 185 is the result of 4 minus 7 times 27. Multiply this out, and we get negative 428,460. Worked out to be exactly the same because, again, that is showing that A and B expressions are equivalent. The difference is that B is in factored form. Professor Kahn's favorite player on the 2023 New York Knicks is a player named Josh Hart. He's my favorite player because he hustles and because he plays hard when he's on the court. Next up, let's look at this rational expression. Let's simplify this rational expression. Remember, the first step in simplifying a rational expression is to factor, and factor maintains equivalency. A quadratic where a is equal to 1, right over here, means that we can factor by first trying to find numbers that multiply to 2. The factors of 2 are 1 and 2, and negative 1 and negative 2. And we're choosing one of these pair of factors based on what they add up to. The sum we are looking for is a positive 3. So since 1 plus 2 is equal to positive 3, that means we can stop right here. We don't have to even consider this because we already found what we're looking for. That was these two factors right here, plus 1 and plus 2. So that means x plus 1 over x squared plus 3x plus 2 is equal to x plus 1 over x plus 1 times x plus 2. So that's factoring. Again, factoring maintains equivalency. And writing this into factored form allows us to identify how to cancel and what to cancel exactly. And our reduced fraction is equal to 1 over x plus 2. So what we are saying here with this is that our original rational expression, A, and our answer, our end result, B, are equivalent. They are the same. That means if we choose, let's choose x equals 1, and let's evaluate expression A. That's going to be 1 plus 1 over 1 squared plus 3 times 1 plus 2. That's equal to 2 on the numerator level. 1 plus 3 plus 2 is equal to 6, so that's 2 over 6, which reduces to 1 over 3. Expression B, 1 over x plus 2, Choosing x equals 1 means 1 over 1 plus 2, which is equal to 1 over 3. And again, we have verified that expression A is the same as expression B through this verification process. Moving along to this. Now before, I made a mistake, and that mistake was that I called this an equation. I caught myself because I do want to make a distinction between the word expression, which we have seen for the first 3 examples, and an equation, what we are seeing right now. The main difference between an expression and an equation is the presence of this equal sign here. This equal sign is given to us as part of the problem, where this equal sign is something I drew in. I drew this in, I wrote this in. And our instructions were not to solve, our instructions were to simplify. Another key difference between an expression and an equation. Now, I'm not saying that they're not similar, I'm just saying that they're not the same. Because this particular example, this quadratic equation, right? When we are presented with an equation, we should make some observations about what we are seeing, what we are given. What type of equation is this? Is this a quadratic? Is it a linear? Is it a fractional equation, something that we have talked about in class? Is it a radical equation, something that we will talk about in the future? All of these are different types of equations that require different types of techniques. This particular example is a quadratic equation. So let's look at some info. What kind of information do we know about a quadratic equation? Right, we know x equals negative b plus or minus the square root of b squared minus 4ac over 2a. That's the quadratic formula. We know, completing the square. We also know about factoring, AC method. All of these are viable methods to solve quadratic equations. Now, like we mentioned in class, factoring is not always possible. When that is not possible, you can either complete the square or you can use the quadratic formula. You can always use the quadratic formula. It will always work. Sometimes, though, if this equation is factorable, it's going to be faster and more efficient of the use of your time to factor it. So let's go through factoring once again. Right, factoring means because a is equal to 1, we're taking this number, negative 48, and we're trying to find all the factors of 48. And we're looking for the one that adds up to a negative 13. 48 has a lot of factors. We see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 factors to consider. And what we're looking for is the sum. And our target number here is negative 13. So let's do a quick addition here. 47, negative 47, 22, negative 22, 13, close, but not good enough. Next one up, 13, 3 plus negative 16 is negative 13. And we have hit, so we will stop right there. We do not need to consider these on the bottom. This is what we're looking for all along. Plus 3, minus 16 is our factors. So again, because a is equal to 1, that means we can open up 2 parentheses beginning with x and x. We can drop in our plus 3, our minus 16, and then we can continue with the zero product rule. Remember when we factored the denominator of that rational expression? We did the same basic steps, finding what multiplies to 2 adds to 3 in this case. We factored it using these parentheses, but we did not use the zero product rule because this is not an equation. This was an expression that we were factoring in order to simplify. But now that we are solving an equation, we're using what's called the zero product rule, and we get x equals -3. And then we get 16 added to both sides, and x is equal to 16. All right, so notice again, we are, let me move this down so I can write something above it. We are taking this equation, x squared minus 13x minus 48 equals 0, and we are factoring it. So what's the first two steps, we're not changing anything. This is equivalent. And furthermore, because this equation is still equal to 0, that means we can continue with the zero product rule after factoring is done. So the last thing I want to discuss today is an expression. An expression is a number, variable, or combination of numbers and variables. And operation symbols. Some examples of an expression, x plus 2, x minus 2. These are examples of binomials. X squared plus 5x plus 6 is an example of a trinomial. And this expression is factorable. This is a factorable expression. Expressions can be smaller, 2x, x over 2, which is the equivalent of 1/2 x. These are monomials. But these are all expressions. When you are working with expressions, very commonly you will see a set of instructions maybe to combine. Combine these polynomials, combine these rational expressions, right? Maybe perform the indicated operation. These are common instructions that you will see. You will often see that you need to simplify, reduce, factor completely, something we saw in this lesson right now. These were instructions given to us for expressions. Now, an equation is made up of two expressions connected by an equal sign. For example, 4x minus 2 equals x plus 2 is an example of an equation because of the equal sign right here. And you will commonly see instructions regarding equations. Solve for x, solve for y, solve for blank. The key word here is to solve because you're solving an equation. An expression has nothing to solve, it has something to combine or reduce or simplify or factor. I hope this was helpful. Thank you for